Okay guys, in this particular class, we are going to talk about indicators, right? And a little more, we're going to learn a little more than is required for our course. Again, the reason why I'm teaching guys this little more idea is because I know it's relevant as far as MCQs are concerned and your practical paper is concerned and the titration graphs are concerned. It's not a big deal. I know I'm teaching you beyond the syllabus. I'm going beyond the syllabus when I'm teaching you guys about PHAs, and you learn that in A2. And similarly about indicators. And indicators, I probably think you won't even learn that in A2 chemistry. But the reason why I'm teaching you guys this again is to understand titration curve. If you don't want to understand titration curves in its entirety, you can rote learn them, then it's absolutely okay to skip this lecture. Okay? Now, okay, let's talk about indicators. Now, what exactly is an indicator? It's just a chemical substance which gives you different colors in different pHs. The moment you have different pHs, it's going to give you different colors, right? And the purpose of an indicator, the actual purpose of an indicator is to show you when the end point has been reached or the equivalence point has been reached. That's the purpose of the indicator. The entire purpose is for, usually it's for titration, right? Because in titration, we want to understand when the equivalence point has been reached, or if the equivalence point has been reached, or the end point has been reached. Effectively, it's what? It's when enough alkali has been added to the burette, from the burette to the conical flask to react with all the acid, right? Or when enough acid has been added from the burette to react with all the alkali in the conical flask, right? It's basically when the acid and alkali are stoichiometrically equivalent to each other, right? That's when we say the end point has been reached, and that's where the indicators come into play, because they actually help you guys understand the end point, or visualize or observe or clearly observe the end point, right? That's the idea behind indicators. And they're just chemical, they're made from chemicals, they are dyes which give you those colors when the pH changes, right? Now, the actual idea behind indicators is that indicators are actually, in reality, and again, not part of your course, but in reality, it's pretty fun to understand. In reality, indicators are weak acids, by the way. In reality, when you make indicators, they are normally weak acid, right? And I can show it to you. This is the symbol for indicator, HIND. This IND is basically the negative ion of that indicator. It's a pretty complicated ion for mostly like methyl, orange, vagara. This is a pretty complicated ion. Instead of writing HA going into H plus A minus, we write HIND. IND, that's just a negative ion. That's it. That's not a big deal, right? And you go into H plus and IND minus, right? Just like when we used to write the general equation for acid dissociation, this is the general equation for acid dissociation. Just instead of A, we are writing IND. That's it. Right? A is the negative ion, IND is the negative ion. That's it. And fun fact, this is my weak acid, right? And because it's my weak acid, this fella right here will undergo a reaction where it will not go into complete dissociation. And the beauty about not going into complete ionization or very slightly ionizing is the idea that this HIND actually has a color. I'll call this color 1. Right? And this IND minus has another color 2, right? And this is, I'm going to actually teach you how indicators work, right? So this particular fella was my acid, and what is this? What is this? If this is my acid, what is IND minus? Now it does not have the ability to give proton, rather it has the ability to take in proton. What is this? This is a base. It's a conjugate base. So basically, indicators are weak acids. Right? And this weak acid in itself, this HIND molecule, this in itself has a color, and this conjugate base also has a color. Right? So this is color 1, color 2. And you could even calculate the equilibrium constant for it, which is K. Okay, I won't go into the equilibrium constant idea. Chhod it. Right? Equilibrium constant idea will get a little too extreme. For all reversible reactions, you could calculate, for all reactions which don't go into completion, you can calculate its equilibrium constants. Right? We can do it. We've learned Kc, Kp. We don't want to care about indicators, but I want to give you guys the idea still. What's the idea? The idea is, let's suppose that you guys have taken your burette, right? You guys have taken your burette, and that's my conical flask. And let's suppose here it's my acid, and here you have your alkali, right? And inside this conical flask, you also had added indicator drops to it, right? Whatever indicator you used, nobody cares. You added some indicator to it. Now, what's going to happen is you're going to have H plus ions dropping. The H plus ions will neutralize this alkali or would react with alkali particles, the OH minus. So H plus reacts with OH minus again and again. After all the OH minus has reacted with H plus, the moment one excess drop of H plus falls inside this or drips inside this conical flask, what's going to happen? Only one drop. And remember, the titration experiment that we actually perform, it's not very accurate. And I'll tell you the reason for it. It's not very accurate because understand that the moment all the OH minus ions have been reacted with all the H plus ions and one excess drop falls, one excess drops of hydrogen ion falls, what happens? The hydrogen ions concentration increase. What would the system want to do? Le Chatelet's principle. What would the system want to do? The system will want to decrease it, or the equilibrium will move in such a manner to minimize this change. And how would it minimize the increased hydrogen ion concentration? How would it minimize it? By shifting the equilibrium to the left hand side. And that's when you see this color. That's when you see this color. Color 1. How beautiful. And for example, you are adding alkali from the burette. And here you had the acid. Now, once all the hydrogen ions of the acid reacted with all the OH minus ion, and the moment one drop, just one excess drop fell inside the conical flask, one excess drop of alkali fell inside the conical flask or drops inside the conical flask, because humans, we are not that accurate. We will see the end point, but the problem is that we always account for a certain degree of error in our titration experiments when we perform them, right? Because the moment one excess drop falls inside this conical flask, what's going to happen? The moment one excess drop of OH minus falls, this excess drop of OH minus is going to react with this H plus, it's going to react with the H plus. Right? And when it reacts with the H plus, what's going to happen? It's going to decrease H plus ions, and the system will want to increase the H plus ion. And how does it do that? It does that by shifting the equilibrium to the right hand side. Right? The equilibrium will move in such a manner to minimize this change. It will shift the equilibrium to the right hand side, and therefore you see color 2. And that's why you've studied these different colors of indicators. For example, methyl orange. All these indicators are slightly acidic. Methyl orange gives you a red color in an acid and a yellow color in an alkali. And the reason for that is this right here. It's literally Le Chatelet's principle. That's it. Yes, normally what happens is, if you want to properly understand this, I would have to write those who are interested, I would have to write the equilibrium constant for you. What is the equilibrium constant? It's basically products divided by reactants, right? So hydrogen ions ki concentration, this I and D minus concentration, divided by reactants, H, I and D concentration at equilibrium, right? That's the idea. And at equivalence point, if humans are extremely precise and accurate, at equivalence point, what's going to happen is you will actually end up with a neutral color, which will be between these two. And that is the reason why, if you perform titration experiment with its utmost precision, which is near to impossible, but if you do it, you're not going to have a red color at the end, because red color at the end means you have one excess drop of acid. Yellow color at the end means you have one excess drop of alkali. But rather, if it's actually bilkul the equivalence point, you're going to have the color between the two, which is orange. And here you go. And that will be the neutral solution for it. And here you go. Let me show you a अच्छा इस ज़बान पे लगाम सुलेमान लगाम. I'm going to show you a beautiful table of indicators. Look at these indicators. See? Now again, please ignore this, and you could see these things. See? Red color, methyl orange, red color, an acid, alkaline yellow. And if it's neutral, exactly, if there are no excess hydrogen ions, no excess hydroxide ions, it'll give you an orange color there. Right? And this is the idea. That's the idea of indicators. Now, you might see something strange here. Forget about this P, K, I, and D. That's not a part of your course. I wanted to explain it, but hey, it doesn't really matter. Just ignore this. This pH range is something which you need to understand. And that is that all indicators have a certain pH range in which they work. For example, you guys in O-levels and IGCSE learned something, an indicator called as methyl orange. You learned in O-levels and IGCSE about bromothiamyl blue. You learned in O-levels and IGCSE about phenolphthalein. You learned in O-levels and IGCSE about other indicators like thymolphthalein, right? Remember? Thymolphthalein, phenolphthalein, right? All of that good stuff. Now, why were you taught? You might have thought to yourself in O-level and IGCSE that why the hell are the examiner making us rote learn so many indicators, whereas we know that all indicators can give you these colors. So why is he making you guys rote learn these indicators? Well, now you know why he did that, because not all indicators work in all pHs. Now, they all have a particular range of pH in which they'll work. For example, if you have a pH of 3.1 to 4.4, this is where you can use methyl orange. Other than this, you can't use methyl orange. You'll have to revert to something else. You have to revert to something else, revert to something else, revert to something else. And the question is, how do we know then? How do we know that for which particular acid-alkali reaction, for which particular titration reaction, which indicator should I use? Which indicator should I use? Right? Because all these indicators, they will not work with the same pH. Now, they have a certain range in which they can work. This will work in this range, 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 this range, this range, this range, and so on and so forth. How do I know to select the proper indicator? How do you know which indicator to select? Well, understand that the correct choice of indicator depends on the strength of the acid and base. It depends on the strength of acid and base or alkali. I'll say alkali. It depends on the strength of acid and the alkali or the base in the titration experiment. Right? So which indicator to actually select for your titration experiment? That you learn through the idea of the strength of acids and bases. Is it a strong acid reacting with a strong base? Then you'll use a particular indicator. If it's a weak acid reacting with a weak base, a strong acid reacting with a weak base, a weak acid reacting with a strong base, all of these combinations you need to learn later on. And how do we learn it? We learn it through the idea of titration curves. So this titration curve actually helps us understand how the pH of a solution varies. How the pH of a solution varies from the start till the end. And once you perform this particular experiment with a certain indicator, you will realize that if it's a strong acid, strong alkali, I'll use that indicator. If it's a weak acid, strong alkali, I'll use this indicator, that indicator. And you can actually cross-check it once you actually understand titration curves. You'll be able to cross-check whether you've selected the right indicator for the experiment or not, right? So it's very crucial to understand indicators, because for your titration experiment, you have to select the right indicator to properly understand titration curves, right? So in order to understand titration curves, you have to select the right indicator. What are indicators? I've discussed it here. They are just weak acids. That's it. And I've discussed a little idea of indicator for you guys, and this is a table given to me right here. And you guys don't need to rote learn this table, but just go over it once or twice and you'll understand it. And that's basically that, guys. That's it. Nothing else. Any question?